In this video, we'll start going over some of the details of finding eigenvalues and eigenvectors and the theoretical results we get from them, and we'll start with real and distinct eigenvalues. So probably the easiest case that could happen for any matrix when looking for the eigenvalues is that your characteristic polynomial factors into distinct linear factors all the way down. So one case is like this matrix here. So say we have matrix A, where the characteristic polynomial is determinant of a minus lambda I, factors as lambda minus 1, lambda minus 2, lambda minus 4. So this tells us here that when I want this to equal 0, that A will have eigenvalues of 1, 2, and 4. We also know that because this is a degree 3 polynomial, that A was a 3 by 3 matrix, which means that any eigenvector we find will be a 3-component vector. And then one last point here is that we know that we will always have at least one eigenvector for each of the eigenvalues, otherwise they wouldn't be eigenvalues. So we know we have 3 eigenvectors, 1 for lambda equals 1, 1 for lambda equals 2, 1 for lambda equals 4. So we end up with 3 of these special eigenvectors. Each of them are 3-component vectors, and since the dimension of R3, or all 3-component vectors, is 3, this means that every basis must have 3 elements. So there's a chance that these eigenvectors that we get, these 3 of them, form a basis for R3, which means I can get every vector as a linear combination of these eigenvectors, and that's going to be super important if we want to do things later on. And it turns out for this case, when I have the different real and distinct eigenvalues, this is always the case. And this idea, with some extra work that we're not going to go in the proof of here, will give us the following result. Let A be an n by n matrix, and assume that the characteristic polynomial for A has n distinct roots, which means we have n different eigenvalues, and because they are all eigenvalues, they each correspond to an eigenvector. So we have these eigenvalues, lambda 1 through lambda n, for the n different roots of the characteristic polynomial. We have the eigenvectors v1 through vn, and the result here tells us that these vectors are linearly independent. And since we have n vectors that are linearly independent, they form a basis for Rn. The key point here is that eigenvectors from different eigenvalues are always linearly independent. So if I build up this set of eigenvectors from different eigenvalues, they all have to be independent. If they weren't, there are issues with how the vectors behave, so they have to be independent, which is great, because then I get a basis for Rn out of the eigenvectors. Now, what does this mean from sort of a computational point of view here? Well, if I have a basis, that means for any vector v, I can write it as v is going to be c1 v1 plus c2 v2 plus cn vn for some constant c1 through cn, because this is a basis of Rn. But with it set up this way, I can tell you right away what A times V is. Because A times V will then be C1 A V1 plus C2 A V2 up to Cn A Vn. But the V1 through Vn are all eigenvectors. So this is easily to rewrite as C1 lambda 1 V1 plus C2 lambda 2 V2 all the way up to Cn lambda n Vn. So if I have this basis of eigenvectors, I can characterize what this matrix will do to any vector just based on knowing how to decompose it into this basis. And this idea would be really helpful when we try to take this information back to use it to solve differential equations later on. Now let's see an example where we work out this type of problem. We want to find all the eigenvalues and corresponding eigenvectors for this matrix: 0, minus 8, 6, 1, 6, minus 3, 4, 8, minus 2. So to find the eigenvalues, we're going to look at determinant of a minus lambda I and see what we get for that. The determinant of a minus lambda I is going to be the determinant of what matrix? Minus lambda minus 8, 6, 1, 6 minus lambda minus 3, 4, 8 minus 2 minus lambda. So we want to find this determinant, and the easiest way to do it is probably to do a little bit of row reduction until we get to a 2 by 2 in the bottom corner, and then use that to compute the actual determinant. So what I'm going to do here is swap the first two rows to get me a minus sign. And I'm going to use that 1 in the top left to cancel out the lambda and the 4 beneath it. So I'm going to do something like row 2 is row 2 plus lambda row 1. Lambda's a constant here, so this is fine. And row 3 is row 3 minus 4 row 1, which will not change the determinant. I'm adding lambda times row 1 to row 2, so I get a 0. I get negative 8 plus 6 lambda minus lambda squared, and then 6 minus 3 lambda. I then get 0 and I subtract 4 from that one. I get 8 minus 24 plus 4 lambda here. That's going to give me a plus 12, so 10 minus lambda. And I can take this determinant by cofactor expansion, where I'll get a 1 from this first term, nothing here, and then I just need this determinant here. This answer here is going to be negative 1, negative 1 to the 1 plus 1, which is even, times AD, so negative lambda squared plus 6 lambda minus 8 times 10 minus lambda, and then minus 6 minus 3 lambda, 4 lambda minus 16. I can do a little manipulation here to make this look a little nicer before I try to figure out what's going on here. I'll leave the negative 1 out front. I end up here a lambda minus 10 when I move the minus sign from here over to here. And then I will see lambda squared minus 6 lambda plus 8. That's a lambda minus 2, lambda minus 4 is how that factors. And then on the other term, I will see a plus 3 lambda minus 6, so that's 3 times lambda minus 2. And then I will see 4 times lambda minus 4. We can actually simplify a lot here before I try to see what's actually happening. I can pull out a lambda minus 2 and lambda minus 4 from both terms to give me a negative lambda minus 2, lambda minus 4, lambda minus 10 plus 12. But that's going to be a lambda plus 2. So this here is my characteristic polynomial, which means my eigenvalues are lambda equals 2, lambda equals 4, and lambda equals minus 2. And I'll label these 1, 2, and 3 so we can keep track of what goes where. Now I want to find the eigenvectors. So for lambda 1 equaling 2, I want to look at the matrix A minus lambda I, and then row reduce it to find a solution to the homogeneous equation for this matrix. In this case, the matrix is minus 2, minus 8, 6, 1, 4, minus 3, 4, 8, minus 4. So I now want to row reduce this because I'm looking for solutions to this v1, v2, v3 equals 0. So all I'm going to make is I'm going to add a column of zeros and row reduce. The zeros don't do anything, so I can just row reduce this as it is. I can first swap the first and second rows, and then I can use this 1 to cancel out the minus 2 and the 4 beneath it. So row 2 is row 2 plus 2 row 1. Row 3 is row 3 minus 4 row 1. Gives me 1, 4, and minus 3. 0, 0, 0. The entire second row goes away, which is good. One of these rows should go away during this process. And then 0, minus 4 of those is minus 8. Minus 4 of those is plus 12 or plus 8. And so this row reduces to 1, 4, minus 3, 0, 1, minus 1, 0, 0, 0. When I swap the 0 to the bottom and then divide 3 by minus 8. So in system of equation form, this says that v1 plus 4v2 minus 3v3 equals 0, and v2 minus v3 equals 0. So here I get that v2 equals v3, and plugging that in up top gets me that v1 should be negative v3. So I can write a vector here that does this. I want to pick any non-zero vector to make this work. So I can pick v1 be the vector 1, minus 1, minus 1. That satisfies these two equations, and so it works as an eigenvector for lambda 1 equals 2. And now we do the same thing for the other two eigenvalues. For lambda 2 equals 4, the matrix becomes -4, -8, 6, 1, 2, -3, 4, 8, -6. We're getting on row reduce. I'm going to do it a little bit differently because I can see right away that rows 1 and 3 are identical. So I'm going to swap rows 1 and 2 just to put the 1 in the top corner. And I'm actually going to use row 2 to cancel row 3 first. And so I'll use row 3 is row 3 plus row 2, the new row 2, to give me 1, 2, -3, -4, -8, 6, 0, 0, 0. And now I can add 4 copies of row 1 to row 2 to get rid of that -4. 1, 2, -3, 0, 0, 6, 0, 0, 0. Now as a system, this says that v1 plus 2v2 minus 3v3 equals 0, and v3 equals 0, because it's 6v3 is 0. So v3 must be 0, which means this term here goes away. And so I'm left with v1 plus 2v2 equals 0. I want to pick a non-zero vector that solves this. So if I pick v2 equals 1, then v1 has to be -2. And so the vector I get here for vector 2 is -2, 1, 0. And then for the third eigenvalue, the matrix becomes this, which you want to row reduce in the same way as before. I'm going to divide the third row by 4 to make my life easier. I'm subtracting 2 copies of row 1 from row 2, so 0. -8 minus 16 is -24. That's a 12. And then I get 0. That minus that is -6. That -3. These bottom two rows are going to be the same again because the first entry is -2 times the second. This will reduce to a 1, 8, -3, 0, -2, 1, 0, 0, 0. So in equation form, v1 plus 8v2 minus 3v3 is 0, and -2v2 plus v3 equals 0. This tells me that v3 must be twice v2. If I plug that into here, that gets me a 6v2. So v1 plus 2v2 equals 0. Or v1 is -2v2. Let's pick that second component to be 1. So v2, 1. I get that v3 is 2 and v1 is -2. So the vector I get, vector 3 for eigenvector, is going to be -2, 1, and 2. We found 3 different eigenvectors for the corresponding eigenvalues. You can check if you want. These vectors are linearly independent, so they form a basis for R3, and would allow us to then characterize how the matrix works on any vector just based on these eigenvectors. That's the idea behind real and distinct roots, how they work, and what kind of problems you can get to solve for using this technique.